Learning.
Welcome to the Spark and AI Summit 2020. This is the What's New in Apache Spark 3.0 training session, and I'm your instructor, Doug Bateman. Just a little bit of background on me. I've been working with Databricks since 2016, and I'm now a principal data engineering instructor at Databricks. And I've been working with data engineering of various sorts and software engineering for roughly 20 plus years in the software engineering industry. I also like to introduce myself as a person, not just your instructor. So I've got two children, one who's 1 year old and another who's 4, and they are lots of fun, and they're being very quiet while we record this session. Thank you guys. And for fun, I enjoy sailing, rock climbing, snowboarding, and occasionally playing chess, although I don't necessarily play it terribly well. But that's enough about me. Let's talk about what we're going to learn today. We're going to start off with performance. We're going to look at what's new in 3.0 and how it's going to make Spark faster, cheaper, and more flexible. Some of the most exciting new features in Spark 3.0 come in this category. From there, we're going to move into usability. We're going to look at what makes Spark easier to use here in Spark 3.0. After that, we're going to talk a little bit about some of the backwards compatibility considerations you may need to face and deal with when moving from Spark 2.0 to Spark 3.0. And last but not least, we're going to look at the broader Spark ecosystem, including where are the developments in Delta, MLflow, and Project Hydrogen. Also, really like to encourage you to ask questions. While the video itself is pre-recorded, we have live TAs available who would love to help answer any questions that you might have. So let's get started with performance. The first and most exciting new performance-related feature in Spark is adaptive query execution. To better understand adaptive query execution, let's look at the historical context. In Spark 1.x, when you wrote a data frame query, it was fed into the Catalyst rule-based optimizer. Later, in Spark 2.x, we introduced cost-based analysis, which would look at file sizes and data statistics that were stored in the Hive metastore to better improve the performance and execution of your Spark 2.x queries. Now, available in Spark 3.0 with adaptive query execution when enabled, you'll also get runtime statistics, looking at the size of the data as it's being processed, so that queries can be rewritten and optimized based on the size of the data at runtime, getting even better performance. To get a picture of how that works, let's first look at the SQL optimization process in Spark 2.x with the Catalyst Query Optimizer. On the left, you'll see that whether you express your query as a SQL query or as a data frame query, it's fed into the Catalyst Query Optimizer as an unoptimized, unresolved logical plan. At that point, it's paired up with the underlying catalog of table names and column names and resolved into your logical plan. From there, a rule-based optimizer that was available in Spark 1.x rewrites the queries, grouping filters together and reordering operations to improve the performance. Then, we can take advantage of cost-based optimization by looking at the underlying file sizes and available statistics to choose amongst many possible physical plans and join strategies. Once we've selected the best physical plan, it then gets compiled into RDDs using what's known as whole stage code generation. And this gets executed. What's missing in this picture is the ability to do any adaptiveness based on optimizations that we can identify at runtime. So starting in Spark 3.0, we have adaptive query execution available to us. I say starting in 3.0, there were small parts of adaptive query execution, in fact, introduced in Spark 2.4 and continue to be available in Spark 3.0, but you'll have to turn it on, and once it's enabled, you'll get the benefit of these features. And later, when we really see the smoothness and robustness of the system, it will be turned on by default for everybody. So how does adaptive query execution work? Well, put simply, as we go about executing our code, we're going to feed back statistics about the size of the data in our shuffle files so that for the next stage, when we do its logical planning, we can dynamically switch join strategies or coalesce the number of shuffle partitions to a more optimal number, or dynamically optimize skew joins or other types of problems that we might identify at runtime. Let's take a look at each of these in turn. So let's start with the first optimization, converting a sort merge join to a broadcast join. In Spark 2.x, this is done by tuning the spark.sql.autoBroadcastJoin threshold, or by using the broadcast hint. This, however, is very hard to tune, and it's affected by changes in your workload, which makes it very hard to maintain over time. And if you broadcast a data frame that's too large to fit into memory, you may cause your executors to go out of memory and crash. Starting in Spark 3.0, we have adaptive query execution. So here we see a case where Spark, by reading the file size, identified that this right-hand child of a join was 15 megabytes, which is above the default 10 megabyte threshold for using a broadcast join. And this is the best Spark could do in Spark 2.x. But in Spark 3.0, when we encounter the shuffle, where once we've read in the right-hand size, after doing filtering from disk, we may discover that the actual size of the data coming in is only 8 megabytes. And at that point, Spark would rewrite the next stage of the plan to use a broadcast join instead of a sort merge join, getting much higher overall throughput. So where sort merge join is great when the two sides of a join are very large, the broadcast join gives us significant performance savings when the one side of the join is less than 10 megabytes or whatever we tune our threshold to be. And here, Spark, in detecting that that right side child after doing a filter is in fact smaller, it will rewrite subsequent stages to use that broadcast join. Another common problem has to do with tuning Spark SQL shuffle partitions. So in Spark 1.0 and 2.0, we just set the default number of Spark SQL shuffle partitions to 200. In fact, back in the days of Spark 1.0, it defaulted to 8, but as we wanted to make sure that Spark worked on pathologically large data sets, that default was increased to 200, and in many cases you even need to increase it above that. This is troublesome to tune, however, because a lot of times we can take advantage of a much smaller number and get better throughput. If you set the number too small, you end up with a lot of garbage collection and spilling to disk. If you set this number too high, then you end up with inefficient I/O as you split up your task into too many smaller tasks, and this leads to increased pressure and overhead in the scheduler. And because this is a global setting, it's hard to tune for the overall query, since each piece of the query might ideally have a different optimized number. And this is particularly hard to maintain over time as new improvements are made to Spark, or as the size of your data set or the nature of your queries change. With adaptive query execution, we can resolve this problem and eliminate the need to manually tune Spark SQL shuffle partitions. How do we do that? Well, here you'll notice that we start out with a very simple query, and as we run the query, you'll notice here in this case we ended up with a shuffle that produced 50 partitions, or 200 in the case of our default. But Spark may realize that these 200 file parts are in fact very small. And so rather than feeding 200 tasks into the downstream operation, Spark can dynamically insert a coalesce operation and decide to coalesce those 50 or 200 parts down to a more manageable number, such as 5 parts, before feeding into the sort stage of the process. This is going to give us much better throughput because Spark is able to dynamically look at the size of those files on disk and choose the optimal number of, or optimal size of those partitions and coalesce them accordingly. Let's look at the next pitfall, data skew. So skew has been the bane of a lot of Spark jobs' performance. When we go to look at data skew, one of the most common problems has to do with long-running tasks caused by partitions being of different sizes in our large operations. So here's a picture. Consider a case where I just did a shuffle or a group by operation on table A. And I've brought all of the items that start with the letter A into the first partition here. You'll notice that this partition is now much larger than all of the other partitions as we go about doing our join operation. As a result, when we go to actually execute, tasks 1, 2, and 3 will complete quickly, but task 0 may take much longer, slowing down the overall execution of our jobs. And this can lead to major performance drawbacks. Compare that to what we get with adaptive query execution. With adaptive query execution, we can dynamically discover in the process of the shuffle, oh, this particular file is too large, and Spark can immediately rewrite its query plan for the downstream stage to split that into multiple partitions, thereby reducing the task size and improving performance as we can spread the load and get the full benefit of our cluster. In regards to adaptive query execution, there are a few configuration settings that you should be aware of. The first is this global setting, spark.sql.adaptive.enabled. It defaults to false, so you need to set it to true if you would like Spark to use adaptive query execution in Spark 3.0. Later, we hope to make this default to true, but only after companies have really tested this in the field and used it in production, and that we know for certain that this feature is robust and well tested. Once it's enabled, there are a few other settings that will control the behavior of adaptive query execution. For example, this coalesce partitions.enabled. Now this will set to true by default, but it still only happens if the global setting has also been set to true. And this will tell it if you've got a lot of small shuffle partitions, please coalesce them into a smaller number of downstream partitions, improving our overall execution speed. And that setting is further refined by these two settings, min partitions and initial partition num. Min partition says if you coalesce, please leave at least this many partitions around. And that defaults to the default parallelism of your cluster. So if you're running in an 8-core cluster, you want to make sure that after the coalesce happens, there are at least 8 partitions remaining so that I can take the benefit of all 8 cores of my cluster and get the benefit of parallelism. Compare that to the second setting, initial partition num. This is how many shuffle files are initially written out by stage 1 before being coalesced in stage 2. So stage 1 will still write out 200 partitions, or really the value of spark.sql.shuffle.partitions. So it's going to write out the 200 partitions, and then they're coalesced at the beginning of stage 2. So this in effect sets the maximum number of partitions that could come out of this. We'll start up with 200, and then we'll coalesce where possible. And how do we decide how many to coalesce down to? That's controlled by this final setting, advisory partition size in bytes, which defaults to 64 megabytes, and it says, I would like each partition to ideally be 64 megabytes if you can make that happen. And you can increase that number if you've got a lot of memory in your computer. So now, let's take a look at a demo. Here, I've got a sample program, and I'm going to read in some data that represents sales data and the cities and where those sales occurred, typical scar schema format. And I'm going to set the number of shuffle partitions to 900 just to enable some contrast. In this first query, I'm going to go ahead and turn off adaptive query execution. And again, off is the default in Spark 3.0. And I'm going to run it the classic way. And the first thing you would notice when running this in Spark 2.x is that this particular query would actually It would run out of memory due to the skew in the sales data. As it tries to group by city, it's going to have some cities make partitions that are too big for the memory available in my executor, and I run the risk of simply running out of memory.
Now, if I add a Databricks proprietary hint for skew join in Spark 2.x, it does execute successfully. This is one of the advantages of using Databricks in Spark 2.x. And you'll notice here it runs and it completes in about 5.5 minutes. Now, let's compare that to how it would behave if I use Spark 3.0 with adaptive query execution enabled. So here I'm going to turn on adaptive query execution and I'm going to enable coalesce and skew joins. So in this case, a hint is not required because Spark can detect the skew at runtime. And you'll notice instead of having 900 partitions as a result of my shuffle, Spark coalesces those partitions down to 397. You'll also notice that fewer total jobs have run. Up here, back when we used the Databricks skew join hint, you'll notice there was a series of jobs that ran before my query really got started, and the purpose of these additional jobs was to detect skew and to figure out which keys were the ones that were skewed. It was essentially a subquery that ran before the original query could then finish executing. So let's take a look at what this looks like in the Spark UI. So on the left, I've got what it looks like in Spark 2.x with the Databricks skew join hint. And on the right, I've got what it looks like in Spark 3.0 using adaptive query execution. It starts out looking very similar. I'm going to read in 100 files for the transaction and sales data, and I'm going to read in 1 file for the city data. But then you'll notice pretty soon I start having some significant differences. First of all, with the skew join hint, Databricks runs that subquery to detect skew and figure out which keys are causing the skew, and then it adds additional columns into the query to allow us to split up that skewed data into multiple partitions, reducing the overall problem of having partitions that are too large. Whereas with Spark 3.0, no such subquery is required. Next, I move into the shuffle stage. So here we begin shuffling our data across disks. And again, this shuffle stage is going to write out 900 files because that's my total number of SQL shuffle partitions. But then at the beginning of the next stage where I do the sorting, notice that Spark 3.0 added this custom shuffle reader that says, you know what, rather than getting 900 files, let me coalesce that down to 397 files. And finally, once the sorting is complete, we feed into our sort merge join. But you'll notice in Spark 3.0, the sort merge join has a flag here, skew equals true. And what the sort merge join will do is look and say, oh, this one file right here is really big. Let me split it up into smaller parts. And so it splits that file up into smaller pieces as it does the sort merge join, so that I can get the full benefit of parallelism in my cluster rather than having one really large task slow down the entire job. Now let's look at another example where runtime analysis can lead to optimizations with adaptive query execution where static analysis could not. In this case, we're going to look at switching a sort merge join to a broadcast join. So here, I'm going to go ahead and set the number of shuffle partitions to 900 again, just so we can see the benefit of the dynamic coalesce logic. But I'm also going to compare how it performs with adaptive query execution turned off compared to adaptive query execution turned on. In this case, my query of the city data frame is going to filter for cities that are in countries to start with the letters A and B, and then I'm going to join it together. You'll notice when I run this with adaptive query execution turned off, it takes 4.6 minutes and produces 900 partitions. Let's compare that to how we do with adaptive query execution turned back on. In this case, it runs in only 2.26 minutes and yields a smaller number of total partitions. Let's see what happened and how that occurred. So we're going to move over here to the Spark UI, comparing without adaptive query execution on the left with adaptive query execution on the right. You'll see here that again, I'm reading in just that one initial file that is 37 megabytes in size. And then we do our filter for countries that start with the letters A and B. And again, we've filtered out the total number of rows. We then go to our shuffle stage, and the shuffle writes out 9.6 megabytes. And over here, 9.6 megabytes. So notice we still did a shuffle in both cases. The difference occurs after that. Once we've completed the shuffle, in Spark 3.0, we get the custom shuffle reader that reports back and works with the underlying adaptive execution framework. And it figures out, hey, because the actual file was 9.6 megabytes, and therefore less than the 10 megabyte broadcast join threshold, we can use a broadcast join. So here we're going to broadcast that data out to all the executors, and we'll use a broadcast hash join. Whereas without Spark adaptive query execution, it would have resorted to doing a full short merge join. So Spark 3.0 was able to, at runtime, figure out that we could use a broadcast join. There is one little tidbit worth throwing in here. Notice that we still did a shuffle before we did the broadcast. Now, if you were to go back to the code and actually give it a broadcast hint prior to doing the join, then it doesn't even need to write out the shuffle files to figure out that it's less than 10 megabytes on disk, and I could save myself a stage boundary. So there is some benefit still to using the broadcast join hint, but the benefit of not using the broadcast join hint is that it will broadcast when appropriate and not broadcast when appropriate. So my code is much more robust. And I think that overall is a win. So 9 times out of 10, I'm not even going to bother using the broadcast join hint if I don't have to. So that's adaptive query execution. It's huge because it looks at the runtime performance of our shuffle files to rewrite our queries. The next performance improvement we're going to look at is dynamic partition pruning. To understand dynamic partition pruning, let's look at how things work without dynamic partition pruning. In Spark 2.x, if I was to write a query, select star from sales, where store ID is 5, Spark will attempt to push the filter down to the underlying data source, and if that data source is partitioned or indexed in some form based on this value, we can avoid reading all of the necessary partition pieces. And this has been available in Spark 2, and it's highly performant and leads to significant performance gains. However, there are a number of queries where this type of optimization doesn't work. Here's a common example, star schema queries. In this case, we're going to query based on city, and then we're going to join our stores in New York with our larger fact table of sales. In this case, we're not necessarily able to prune the partitions of our larger fact table because it's not organized by city. And this leads to significant loss in performance. People used to resolve this type of problem by pre-joining those two tables together and writing out a larger joined table to disk that we could then query. And we could then get the benefits of partition pruning based on city. But this had a number of drawbacks, not the least of which being the time it takes to maintain this denormalized table and the size on disk when you have a denormalized table with multiple dimensions. With dynamic partition pruning, we solve this problem. And the way it's solved is our dimension table is queried, in this case for stores that are located in New York. So we're going to filter all the stores that are located in New York and identify those store IDs. And if the number of store IDs is below our broadcast join threshold, we can broadcast out that list of stores over to the other query that's going to be reading those stores from our sales table. And now we can look at the partitions that are related to only those store IDs in New York. So if my underlying data source is able to index or be partitioned by store ID, either through Z-ordering, column-based statistics that are stored inside of the Hive metastore, or with partitioning itself on the underlying Parquet file, we're going to be able to prune the partitions to only partitions that have store IDs that matched the New York query. At that point, we then scan our fact table and we could do a much faster join. This leads to significant performance improvements. If you look at how we do in the TPC DDS query benchmark, you'll notice a number of our queries got very large improvements. One of them got, in fact, a factor of 18 in terms of improvements. Others got improvements of 8 to 10 times improvement. This is huge. In terms of configuration, you'll notice in this case, the Spark SQL Optimizer Dynamic Partition Pruning.enabled setting defaults to true. So you don't even need to enable dynamic partition pruning in Spark 3.0 to have it work and start accelerating your workloads. However, if you experience difficulties, you can always turn it off. Now, let's look at a demo. So over here, we have the query that we just saw previously, where we're reading in our city data and our sales data, and then we're joining them for countries, where the country starts with either the letter A or the letter B. And we're going to compare two different data sets. In one data set, the underlying sales data is not partitioned in any particular way. In the other data set, the underlying sales data will be partitioned by city, but not by country. And yet we want to be able to take advantage of this filter by country as part of the city query and gain the benefit of dynamic partition pruning. Now, when the data is not partitioned by city, I'm not able to take advantage of dynamic partition pruning. And you'll notice that the underlying performance is 2.26 minutes. When the data is partitioned by city, then I'm first able to query and find all of the cities where the country doesn't start with or starts with the letter A or B. And if so, I'm only going to want to read those partitions in the underlying sales data. And in this case, we look and we see that this performance dropped by a factor of 4 to 5 down to under 30 seconds. Let's see how that looks in the Spark UI. So here in the Spark UI, you'll see the unoptimized case. We simply read in our sales table, and it reads in 100 files. In the optimized case with dynamic partition pruning, it first executed a subquery to determine all of the partitions that would deal with cities that are in countries that start with the letter A and B. So you'll notice here, there was this entire subquery that first ran to figure out which partitions or which cities are in countries that start with A and B. And then it only reads those partitions of the larger table. So here, I only read in 27 files as opposed to the original 100. After this initial optimization, where I read in a fewer number of files from my large fact table, I can then scroll down and see that the rest of the query is very much identical, all the way to the bottom, including the fact that we're still using the previous optimization we discussed, where dynamically we can determine that we'll use a broadcast join as opposed to a sort merge join. But that one difference of reading 27 files instead of 100 files gave us that performance boost of 4 to 5x in this case, using a dynamic partition pruning. Now, let's look at the next opportunity for performance gains that are available in Spark 3.0. In Spark 2.x, you were able to provide a broadcast join hint to recommend a specific join strategy. But there were other join strategies that might yield performance gains, such as a shuffle hash join, and you weren't able to provide hints for these types of joins. Starting in Spark 3.0, you're going to be able to provide hints to specify the join strategy of the underlying physical plan whenever the actual adaptive query execution engine doesn't quite give you what you want. If you want to take manual control, you'll have more freedom to do that now with hints. So let's quickly look at each of the different types of joins and just discuss some of the benefits and trade-offs. The most common type of join in Spark is the sort merge join. The sort merge join is the most common because it's the most robust. It works when you're joining two very large tables. And it works by sorting both the left and the right side of the join, doing a full reshuffle and sort, so that then we can read in each row, row by row, and match them up to accomplish our join. It scales to very large data. The downside is that it can be slow when you're joining small tables. The sort is overkill. The second join type that's available in Spark, but in Spark 2.0, had fallen out of favor due to concerns about scalability and memory pressure, was the shuffle hash join, this third one on the screen. This one was very similar to a sort merge join in the sense that it did a shuffle, but it didn't bother actually sorting the data during the shuffle. Instead, it would read the data into a hash table. This skips the sort step, but has the downside that that hash table has to fit in memory. So if the data is skewed and one of these the shuffle causes the sort to be split up in such a way that one partition is too large, you might end up with an out-of-memory error. And this is why Spark 2.x tended to prefer the sort merge join. The third type of query that we look at in Spark, or a third type of join that we look at in Spark, is the broadcast hash join. The broadcast hash join is very fast and works when you're joining one large table with one very small table. And by default, small means less than 10 megabytes, although that parameter can be tuned. In this case, the small table is broadcast to all of the machines in your cluster and joined with the relative parts of the bigger table. This results in no need for a shuffle, no need for sorting, and is very, very fast, but only works when one of the tables is small. And then the last type of join is the least performant. It's the shuffle nested loop join. In this case, Spark simply takes all of the different combinations of the left and right-hand side, and it can, through a nested loop, look to see which ones match up. The benefit of the nested loop join is that it works when you, for example, use a user-defined function to determine which rows of the left and the right should match up. The downside is that it's extremely costly as its performance is n-squared. You have to look at every row of the left side to every row of the right side, which can be very, very expensive. So in Spark 3.0, we can begin to specify which of these methods we want to use. For broadcast joins, we can use the typical broadcast hint that's been available even in Spark 2.x. And there are several different aliases that will accomplish the same thing when it comes to that hint. But now in Spark 3.0, we could specify a hint for when we want to use a sort merge join. Any of these values will accomplish the sort merge join hint. Or if we know that our data is well distributed, we could say, look, let's use a shuffle hash join and avoid the cost of a sort, in which case we could provide the shuffle hash join hint, or the nested loops join hint, if we were going to do a nested loop join. So this gives you a lot more flexibility, although ideally you'll never need to provide these hints because you'll use the adaptive query execution instead. And last but not least, I do want to point out that you can also provide these hints in the DataFrames API by going dataframe.hint and putting the hint on the particular part of the table that you're joining. So in this case, I'm reading the first table. I specify a hint before I do the join with the second table. So this covered all the performance gains that we're going to highlight in this session on Spark. Now, let's take a look at some of the usability improvements that are part of Spark 3.0. The first one, and it's the one that has me the most excited, are the improvements to the Explain Plan feature in Spark. So if you've worked in Spark 2.x, this screen should be very familiar to you. Here, we're looking at the underlying query plan, and you'll notice that we've got the hierarchical. I'm going to read a query, provide a filter, aggregate that data, and then filter out the cases where the max value is greater than 0. You'll note by the time we get down here to the optimized logical plan, and in fact, eventually to our physical plan, lots more data gets added, and these queries can become incredibly difficult to read on the screen, especially if your query is joining 20 or 30 tables and doing a lot of various operations. This chart can be very hard to read. So starting in Spark 3.0, we have a new type of explain plan called explain formatted. And if you do explain formatted and provide your query, it will now rewrite the formatted plan like this, where you see the entire tree view at the top with numbers that now index and provide more detailed value down here. So you can see the forest through the trees at the top, get a sense of the overall query, and then as you want to navigate this and get more detail, you can come down and look at each individual row. This allows us to provide a lot more information and a lot more detail in the explain plan without causing this unwieldy level of nesting when we're looking at really, really large queries. Another big benefit of explain formatted is that subqueries are going to be broken out and shown separately. So in this case, if I've got a subquery inside of my larger query, you'll notice that I'll get to see its underlying plan displayed cleanly here. And this makes for the overall query to be much easier to read as you're trying to analyze the underlying query plan in your Spark 3.0 queries. Next, let's look at the improvements to the Spark UI, especially in the area of structured streaming. So if you use the new UI, the Spark UI in Spark 3.0, you're going to notice a new tab up here in the top, Structured Streaming. This will allow you to see all of the underlying running continuous queries, your structured streaming APIs, your completed queries, and when you click on a given run ID, you can drill down and view metrics to view the health, the performance, the input rate, the processing rate, and so forth of your queries. But one of my favorite new improvements in Spark 3.0 is the documentation that you're going to see to go with this in the Spark 3.0 documentation. So here's a preview of the Spark 3.0 documentation for Spark 3.0 Release Candidate 3. And if I come over here to More and click on Monitoring, you'll notice this link here to documentation on the Spark Web UI. As you click on the documentation, you'll notice that I can now get details about every box and every value that you see in the UI. It used to be that if you wanted detailed information about what you could find in the Spark UI, you had to go and take training from a company like Databricks. Now it's well documented and available to the world. So let's now click on the Structured Streaming tab and view. We can see the inputs, the processing rate, the input rows, the batch duration. I can see the overall performance of each of my queries as they run through the Spark 3.0 API, and each of these metrics that I'm able to see has a detailed explanation. This is huge. I not only have more information in my UI, but I have better documentation to go with it. One thing I do want to call out is don't confuse the new Structured Streaming tab with the older tab called Streaming. This has to do with dstreams. And this is one that we're really hoping nobody these days is using dstreams. The naming can be a little bit confusing, and I'm hoping that gets renamed before they release the final version of Spark 3.0. Now let's look at another new exciting usability improvement that's available in Spark 3.0, Pandas UDFs. So Pandas UDFs were introduced initially in Spark 2.3. And you'll notice here that it was written to work in Python 2, and we added information about the underlying data type, for example, that this is a scalar value being passed in. We provided this type of information inside of the annotations so that we could have a UDF that used the underlying vector compute engine of Pandas. In fact, they used to be called, or we still technically call them, vectorized UDFs. But what we've noticed is Pandas UDFs, it's a much more friendly name. Pandas are cute and cuddly. Vectorized UDFs, they sounded very mathy. So we say Pandas UDFs. And the idea is that I'm using Pandas to be able to do batch bulk vectorized computation under the hood inside of Spark to get big performance gains. Now, in Spark 3.0, we're going to move the default programming language that we expect to be Python 3. And if you're using Python 3, well, then you should be using Python 3 type hints. So if you use the Python 3 type hints feature, some of the information that we used to have to include in the annotations is no longer necessary. And this just leads to more readable code. So let's take a look at some examples. Here, we're going to look at a group by operation in Python. So I'm going to do dataframe.groupby, and I want to call apply in pandas. Notice that I can now say apply in pandas and pass in a lambda function, or really just a simple Python function, and we're going to read the type hints to understand what type of data is being passed in. So this apply in pandas is going to make use of the type hints so that we don't have to provide that type of information in annotations. Now, let's look at one more improvement that's really significant in Spark 3.0. And this is improvements to data source v2. So data source v2 has been around for a little while, but it was still marked experimental. And what data source v2 does, and I really want to call this out, is that it adds a lot more information about the underlying data source that you're querying to allow for significant performance gains. So the catalog that's available in the Hive Metastore provides limited information that's not necessarily everything that we want to know. And we'd like to be able to read other types of external data stores. We want to be able to read Parquet files. We want to read Delta tables. We want to be able to do operations like altering tables and dropping tables. And this is what's been added in the data source v2 API, and it's been marked experimental. This API is now starting to mature and stabilize. So certain parts that had been marked experimental are no longer. Other parts have been improved and expanded and are still experimental in Spark 3.0. This is going to enable us to query the data source for all sorts of information. For example, when we go to query Delta Lakes, we want to be able to do predicate pushdown and partition pruning using information that's now made available through this v2 API. The reason this is significant is people who are creating connectors to other types of data sources really should start using Spark Data Source API version 2, as opposed to what a lot of people have been doing with version 1. This provides huge improvements. One of the biggest ones being, of course, in Spark 2.0 or 2.x, we were able to use a unified API for streaming and batch. And this was made available through the improvements of these v2 APIs. So if you are working on any type of connector for your data source, Now is the time to start looking at using the V2 APIs. There's one big improvement in the V2 API that I really want to call out, which has to do with the customized catalog plugin. The catalog API defines how Spark looks up tables in any kind of Spark connector. And you'll notice here that we can do streaming readers, we can do batch readers, all sorts of different readers and writers, and this type of information has gradually been maturing and improving, and we really want to push the community to start using it. Now, if you are not creating your own connectors, you're just going to start getting the benefit of the fact that other people are creating their connectors that use this V2 API. So if you're just a consumer of Spark and you're not writing your own data sources, you don't need to do anything to start taking advantage of this. If you are creating your own connectors, there is this important slide I want to call out. When should you use the V2 data source API? Number one, use it if you want to provide the added catalog functionalities for things like predicate pushdown, table alterations, etc. That wasn't available in V1. Use the V2 APIs if you want to support both batch and streaming. And use the V2 APIs if you're sensitive to performance because of the amount of information that's now available in terms of data partitioning, partition skipping indexes, vectorized readers, and all sorts of other pieces that are now available. The one caveat again is that it's still being improved, so it's not quite as stable as V2, but one of the exciting things in 3.0 is the fact that it really is maturing and a number of interfaces are no longer marked experimental. Now, let's move to the third part of our training presentation and talk about compatibility considerations. So Spark 3.0, first of all, only builds with Scala 2.12. So we are no longer supporting Scala 2.11. Now, shouldn't be too big a deal because your code that was running and working on Scala 2.11 should work on Scala 2.12, provided that any libraries that you're using have also been updated and compiled for Scala 2.12. Another big change in Spark 3.0 is that we're deprecating our support for Python 2. Well, Python 2 was already end of life. If you haven't moved to Python 3, you really should consider doing so. The other item that's really worth calling out is that Spark 3.0 adds support for a lot of newer versions of Hive and Hadoop. So we can now support some of the newest versions of the Hive Metastore, including the Hive Metastore version 3.0, which should improve your ability to integrate with other products when using Spark. And then last, I really want to call out the fact that Spark has finally moved beyond Java 8. So for a long time, Spark had not been able to move past Java 8 due to the way that it worked with native rows and native code. A lot of that work has gone into really improving that, so we can finally use things like Java 11, and we can use the G1 collector, which should give significant performance improvements to your Spark applications. Other changes. So I already mentioned the Spark core has been built with Scala 2.12. Your code that was written before should compile just fine in Scala 2.12 in terms of the Spark APIs. So the only key thing is making sure other code, for example, libraries that you're using, have been recompiled for Spark 2.12 or Scala 2.12. Other big changes, well, this is a small change. The event logs are now automatically using UTF-8 encoding. It used to be the case that when Spark did logging, it wrote those log files using the default character set of the Java virtual machine, which meant that if you were writing tooling designed to parse those logs, you couldn't rely on what character set you were reading. Common sense, let's standardize. We're going to write out UTF-8 in all of our log files unless you specify otherwise. Nice improvement in Spark 3.0. Other changes. Stricter enforcement of Spark configurations. So Spark used to be somewhat forgiving. If you put invalid entries in your Spark configuration, for example, you set keys to invalid values, sometimes Spark would ignore those invalid values and run anyway. Spark 3.0 is moving to a fail fast mindset. If it reads an invalid entry in the configuration files, it will generate an error. Now, this is only going to impact you if you had invalid config files in Spark 2, you move to Spark 3, you're going to discover that you had an invalid config file, and you're going to get an error where you didn't before, but you should be fixing that problem anyway. So this is one of those cases where even though you'd have a portability issue moving to Spark 3.0, it's a good one. It's telling you fix your mistake. We like that. And last but not least here, there was a feature that's been in Spark for a very long time, but has been discouraged. It was added in Spark 1.x. Spark.driver.allow multiple contexts allowed you to create and instantiate independent, different Spark contexts. That's not desirable. It's been deprecated. It's not something that anybody should still be doing because in Spark 2.0, we added the new Spark Session API that allows you to create subsessions so you can have multiple independent sessions, each sharing the underlying Spark context. There's no reason to be creating and instantiating multiple Spark contexts anymore, and Spark 3.0 is going to officially deprecate the setting that would have allowed you to do it. A few other things that have been changed, just a few method renames. Number one, shuffle bytes written. It's just been renamed to bytes written. Shuffle bytes write time, renamed to write time, and so forth. A few of these renames, they shouldn't affect a lot of people, but it could affect you if you've written some of these listeners. The other thing that's worth calling out here, there was a code in task context called is running locally. That turned out to be a bad idea. You really want your code to run the same, whether it's running in local mode or remotely, so that's been removed. And other pieces as well have been disallowed or made deprecated. And last but not least, there's some improvements in the accumulator APIs that improve the underlying behavior. And I'll let you read about those if you're still using accumulators. A few other things here. Some of the functions have been renamed. A few other small changes. And if you need to access legacy behavior, you can actually still import it. Spark.sql.legacy. And you can import and access some of the legacy names of things. Another big change that's been made has to do with SQL compliance. For example, come down here. It used to be that in Spark, if you used the trim SQL function, you would give it the characters that you're trimming off and then the string. But ANSI SQL, everybody else in the SQL world, had the order reversed, where you would go trim, give it the string, and then the characters you want to strip off. Spark was the outlier, and it wasn't ANSI SQL compatible. So Spark said, all right, we're going to go ahead and fix it and be compliant with the rest of the world so the people who are lifting their workloads and bringing it to Spark will be able to use that without having to make changes. However, if you're moving from Spark 2.0 to Spark 3.0, you're going to need to make sure that you update trim if you're using SQL. If you're using the data frames API, it's not as big a deal. Similarly, type conversions have been made ANSI SQL compatible when inserting new values in a column. So this is really, really nice, the fact that we're enforcing more parts of the ANSI SQL standard, but it may mean that you have to make some corrections to some of your queries. A few changes to Spark ML. The biggest one here, I like a lot, is the string indexer. If you've been doing any type of machine learning, you'll be familiar with the string indexer, which allows you to take a string column and instead replace it with numeric values. For example, hot, cold, rainy, sunny, and snowy would become 0, 1, 2, 3, and 4. Well, the annoying thing about the string indexer is you had to apply one for every single column that had strings, which led to really, really long pipelines. It was just verbose and it didn't add any value. So starting in Spark 3.0, the string indexer is able to take multiple column names as input instead of just a single column name. And this makes it so much more readable. You'll just have one string indexer instead of 20. And that one string indexer would index all 20 columns. Another change has to do with the one-hot encoder. In Spark 2.3, we deprecated the old one-hot encoder. It was a transformer instead of an estimator, and that turned out to be the wrong API for it to have implemented. So the one-hot encoder was rewritten and called one-hot encoder estimator. The problem was nobody rewrote their code, and everybody was still using one-hot encoder, which was a transformer. Now, that's no longer an issue. We simply are going to deprecate and remove the old one-hot encoder that was a transformer and only give you the one-hot encoder estimator by renaming the estimator to the original name. So now the whole world should be using the newer version of the one-hot encoder starting in Spark 3.0. You won't have to remember to convert it code to say estimator anymore. The flip side is if you were very diligent and you used to say one-hot encoder estimator, you will need to make that change manually one more time. A few other changes. PySpark, we're now supporting, of course, Python 3.0. Pandas, you're going to need Pandas 0.23.2 or higher. And if you're using Arrow to convert between Spark and Pandas data frames, PyArrow version 0.12.1. Now, keep in mind, these are not breaking changes, but if you want to use any of the new features, you will need these newer versions of the libraries. If you're using Spark R, there's a few changes that you should be aware of as well. In Spark, moving from Spark 1.0 or X to Spark 2.x, the Scala and Python APIs had a lot of methods that got renamed and really improved readability, including the introduction of the Spark session and the reader and writer frameworks. And similarly, register temp table had been renamed creator replace temp view in Spark 2.x. Python and Scala got these changes, but for some conspicuous reason, Spark R did not. Spark R was just too new and still being developed at the time. Well, it's been post-due, and finally in Spark 3.0, Spark R is catching up and getting those method renames as well. So if you're using Spark R, you will need to update your code to use these new method names. Once you do, you'll be good to go with Spark 3.0. So that completes our coverage of some of the big compatibility changes in Spark. The last part, I really want to talk about what's changed outside of core Spark and in the broader ecosystem, and how Spark is embracing the broader ecosystem. So to do this, I want to look at a few projects, the first one being Project Hydrogen, which really helps Spark integrate with the broader ML ecosystem. And this is huge. Now, Project Hydrogen is technically older than Spark 3.0. I really should be calling this talk What's New in the Past Year, not just What's New in Spark 3.0. This was actually introduced in Spark 2.4, and the goal of Project Hydrogen was to enable first-class support for all distributed ML frameworks within Spark. How did we do that? Well, the big problem we had in Spark was Spark's execution model didn't work well with a number of ML frameworks execution models. What do I mean? Well, in Spark, when a stage run, each task executes independently. The idea is to get massive parallelism and fault tolerance. If one of the tasks failed, we simply rescheduled that task on another executor. And this execution model has worked great for Spark, but it wasn't compatible with how a framework, for example, TensorFlow works. In TensorFlow, the tasks all run and talk to each other and exchange information. There's a lot of coordination between tasks, and we have a lot of optimization, and therefore if one task were to crash, we would have to rerun all of the tasks. So how do we take a framework like TensorFlow and make it work in Spark? Well, Spark introduced with Project Hydrogen the barrier execution mode. In the barrier execution mode, Spark is able to transition from its highly parallelized throughput model when it's doing data manipulation to instead support these long-running, interconnected communicating tasks that are needed to run something like TensorFlow. You get gang scheduling. It's going to simply run these long-running tasks with a barrier until that stage completes, and then we're going to resume normal embarrassingly parallel high-throughput Spark execution to consume the results. This is huge because it means that Spark now has better integration with machine learning frameworks than ever before. Another big gain that comes with this in Spark 3.0 is accelerator-aware scheduling. So a number of deep learning frameworks are able to use GPUs, for example, TensorFlow. And if you were using a cluster manager like Yarn or Kubernetes, and you wanted to launch Spark, you needed to be able to specify that your Spark job should be requesting GPUs from Yarn or Kubernetes. Spark 2.x supported these cluster managers like Yarn and Kubernetes, but it wasn't aware about the availability of GPUs, and it couldn't specify that it wanted to request or prefer GPUs over other CPU types. Spark 3.0 now solves this by giving us the ability, when we bring up our application, to specify that we would like to request GPU resources from our underlying Yarn or Kubernetes clusters. So this then lets us take our deep learning workloads and run them on GPUs. And this works inside of standalone Spark scheduler, the Yarn scheduler, the Kubernetes scheduler. And the one caveat is that it works at the application level. That is, when you bring up your Spark application and it first requests resources for its executors, this is where we are currently specifying that we want a GPU. That means that there is future work available to us to be able to actually allow us to have individual tasks prefer a CPU or a GPU on a task-by-task or a job-by-job basis. That's not available today, and it's left for future work, but it's something we definitely want to do. Today, you can still get GPUs at the application level in Spark 3.0, which is huge. So that was Project Hydrogen. Let's now talk about Delta. So if you went to Spark Summit last year, you would have heard a lot of fanfare about the open sourcing of Delta Lakes. Delta Lakes is a huge complementary technology to Spark. It's a file format that improves upon the Parquet file format, adding ACID transactions to get the scalability and throughput benefits of Parquet with updates and transactional benefits that we need for a modern data lake application. To better understand why Delta is such a big deal, it helps to understand some of the top 10 big challenges people had without Delta when building a data lake. Number one had to do with appending data. If people were appending data while you were busy reading, you could get incorrect reads. Number two, modifying existing data would be extremely difficult. You would have to copy the entire table, modify the rows that you wanted to change, and then stop all reads, copy the new data in, and then resume again. Modifying data was very difficult in a traditional data lake. And if you were adding new data to a data lake and a job that's writing to your data lake failed, you would have problems with corrupt data where half the data is there and the rest is missing. Other problems that you would have in a traditional data lake would be keeping it updated with real-time operations. If you were doing batch and streaming, you had to use something known as Lambda architecture so that you could keep your data up to date as new information arrived. But this led to duplicate logic and a lot of time-consuming code and inconsistency. Other problems that we had with data lake included, or data lakes in general, included keeping historical versions of the data. You've updated your data lake, but now I want to go and see what my data looked like last month so I can figure out why the machine learning model is predicting what it's predicting. Metadata itself is a challenge in any data lake. The metadata itself can become large with thousands of tables and thousands of partitions in each table, and this itself becomes difficult to scale and manage. If you're building a data lake, one of the biggest, most common problems and a total performance killer is what's known as the too many small files problem, where your data lake has constantly been appended to, and you end up handling millions of small files, killing the overall read throughput of your queries. Another big challenge that people who are building data lakes would have to deal with would be fine-grained access control. I want to be able to have access control on rows and on columns. How do we do this in an enterprise way? Similarly, performance, partitioning the data. You end up with difficulties in terms of keeping those partitions up to date. Performance of partitioning the data is error prone. You can end up having too many partitions, which again will slow down your overall throughput. And last but not least, data quality issues. Ensuring that you can update and migrate and evolve your schema over time so that your data is correct and has high quality. And so Databricks created and then open sourced Delta Lakes and announced it a year ago to great fanfare as a new way of approaching building data lakes to address that top 10 list of big challenges and problems. And it's based on the Parquet file format. It's open source, and what it adds is a transaction log so that you can bring the best of data warehousing to the best of data lakes. And you can use Apache Spark to get that scalability by adding reliability, quality, and performance to your data lake. So what does that look like? Well, if you look at this first list of items that I mentioned in terms of the challenges, hard to append, or halfway written jobs, or that fail midway, or keeping historical versions of the data, we're going to add ACID transactions and a transaction log that's going to allow me to only read new records if the entire write was successful, and to deactivate old partitions when new partitions with new data are available. And then go back in time and read what the data used to look like by reading historical partitions as necessary. Similarly, we're going to address challenges 6 and 7 that have to do with performance around metadata by using Spark itself to read and write the metadata for our data lake. And we're going to address the too many files problem with commands like optimize and vacuum to group together small files and to reindex them and order them so that we have larger files. This is a feature that Databricks has had in its enhanced version of the Delta runtime. We call that the managed Delta Lakes. Similarly, Databricks is adding on top of Delta Lakes role-based access controls and access control lists. So if you run your Delta Lake on Databricks, you get the benefit of that feature. And then in terms of data quality, this is available even in open source with schema enforcement and schema evolution. And this is huge, the ability to use Delta Lakes to really improve. But this is old news. What's new in the past year? What's new about Delta Lakes in this past year is the amount of industry adoption and integration. So we're seeing a lot of different technologies and partners out there integrating with Delta Lake so that and connectors existing so that we can use and connect Delta Lakes and ingest Delta Lakes into Snowflake or read from Snowflake to populate my Delta Lake. Similarly, connectors so that Delta Lakes can work with Athena or Delta Lakes can read and write to Redshift. Here's a list of a number of partners that have been building and creating integrations with Delta Lakes, including Azure Synapse Analytics, Informatica, and Tableau. And companies that are adopting Delta Lakes for their large data warehouses. So in the past year has been a huge shift. Whereas a year ago we were announcing this open source project, now we can really look and see the maturity of this open source project in terms of industry adoption. And this is huge. If you are not yet using Delta Lakes, we really recommend you go to delta.io and take a look. The potential to improve the performance of your Spark applications is enormous. Next, let's take a look at MLflow. So MLflow was another open source project that was announced, and it has gotten huge improvements in the past year. One of the biggest that I really want to call out is this model registry. But before I do, I want to just look at what are all the parts of MLflow now. So MLflow started out with MLflow tracking, which lets you log your machine learning experiments and see which models produce the best results with which hyperparameters. Then we had MLflow projects added, which allowed you to essentially create workflows that say, run this machine learning step, now do this machine learning step. You can package up your machine learning pipeline so that you can run them anywhere. And MLflow models created a portable file format for saving and serving your machine learning models outside of Spark. And now what's been added is really cool, the MLflow model registry. And I'd like to show you what that looks like. So here's an example of Databricks. And if I come down here to the MLflow model registry, I'm now seeing the open source screen that's part of the open source MLflow project. And I can see models that I have chosen to deploy to my registry. And what I can do is take any model, and I can actually tag versions of my model for production and staging and manage the life cycle of these models as they go from training to actual production code. So what the model registry lets you do is take models that you would have done for your experiments and eventually put them through a version control system as you push them out to production deployments. And you could take a given version of the model and then change its state and say, you know what, I'm ready to transition this model into production. This is huge. So lots of big improvements in MLflow in terms of model serving using REST APIs, model registry for maintaining and managing the lifecycle of your models, built on top of all of the core of MLflow that we've been using and loving for the past year. Highly recommend, if you're not currently using MLflow for your machine learning experiment tracking, that you check it out. Some of the big benefits now of the MLflow registry. Number one is this hub. It allows, essentially, if you are publishing models to other people at your company, you now have a hub for collaboration where people can come and see what models are available, and you can manage the life cycle of those models to improve the reliability of your overall model deployment process. And it gives you this visibility and governance into those MLflow models. Really, really big. Highly encourage you to do it. This other chart I really want to point out to you is the adoption of MLflow. So MLflow has gained more contributors in a year than PyTorch got in 4 years. So here's PyTorch, and here's the growth rate of MLflow. And it was just downloaded 1.7 million times per month as reported by the PyPy package index. That is huge. And this brings us to the conclusion of what's new in Spark 3.0. I really want to thank you for your time today. I highly recommend you attend a number of the What's New in Spark 3.0 sessions, and I really want to thank you for attending. Before you go, feedback is very important to us. Please go back to the conference meeting play application and click on the feedback tab and give us feedback about what you thought about this training. What can we do to improve it? What can we do? What did you like? What would you change? Thank you very, very much. We would love to get 90% feedback, and that means I need you to take time right now to do it. And finally, I would like to thank the contributors who made this training possible, including the Spark 3.0 team, especially Zhao and Michael, who have really made sure that we can communicate to you what is new in 3.0 and put it in a powerful context. And especially the Databricks curriculum team, including Kate Sullivan, who put together this entire presentation and spent endless hours researching what's new in 3.0 and working with the Spark 3.0 team, and Jacob Parr, who built the demos that you saw today. It is an amazing team here at Databricks, and we couldn't have done this without. Thank you guys so much. With that said, enjoy the conference.